Okay, so the final week before we all die. um, now, so as far as the final goes, so today's the last day, presumably, that I'm covering anything. It's going to be about time-dependent PDEs. We've been doing. I think we've seen enough of Poisson's equation for a lifetime. So I can talk about time-dependent case and certain methods that are used for that. And I will ask some questions about these for the oral. Again, it's like conceptual things. And this is from chapter 5 from the notes. So we have all of this week, next week, with finals and commencement going on. But so what you can do is just we can figure it out individually. Just what works for you, because you might want to have more time and either you might want to get it over with, or a little wait till the end to give you more time because if you have other stuff like 771, or whatever else you have. Okay, or 560. Well, you get a 560 final out of the way this week. Okay. Sorry if I was an upsetting thought, but okay. Okay. Yep. Okay. Yep. There you go. So and now I got to grade it. Yeah. So we're all in misery. Actually, grading would be pretty easy for this class. It's everything else that's going to be. Yeah. So just let me know what you want to do, because really, anytime after today, you'll have seen everything, but beyond it. I'm recording, right? Okay. Yeah. Now, as far as what I would ask, we've covered a number of methods for different things like finite difference versus okay. Okay, so things to look at is there's different classes of methods that came up. Finite difference versus spectral. Just for PDEs in general. Okay, we also had for linear system, AX equals B problems that come up from PDEs and ODEs. We have direct methods, iterative methods. With iterative methods, we have stationary methods, or Krylov subspace methods, or multi-grid methods. Okay.
Those all fall under linear?
Yes, so in fact, these three all fall under iterative. Okay, whereas direct subsumes Gaussian elimination, Cholesky, etc. And then we'll see today for time-dependent PDEs that become systems of ODEs. Methods I will talk about, one step, multi-step. I think that's pretty much all. Okay. Oh, yes, it is. Okay. One step would include mainly Runge-Kutta methods. Multi-step includes Adams methods. This is all from what's coming up today. Okay. So there are different problems or subproblems that came up because PDEs, if they're time dependent, become a system of ODEs. If they're time independent, they become a AX equals B problem. And in both cases, you have various methods to choose from. So I bring up these different classes methods because it's important to know the relative merits. What's the advantage of using spectral method versus finite difference? What's a limitation of spectral so that you wouldn't choose it all the time? I always like to ask questions about when would you choose one method over another? What kinds of problems can a certain method be used for? Like if I have an AX equals B, I can't just go ahead and use Cholesky. You can only use that in certain situations. Things like that. All right. Dang it. Other concepts that have come up, I mainly talked about them with regard to finite difference methods, but as you'll see today, they come up with methods for ODEs also, or error analysis. We have these fundamental concepts: consistency, stability, and convergence. Okay. And how they relate. For example, there's the Lax equivalence theorem that relates all three. Now, there's also local truncation error and global error. So, what's the difference between them? For a given problem, how would you get the local truncation error? I may ask questions that tie into certain parts of a homework. No, I'm not going to ask you to write MATLAB code on the board. But trying to think of what would a good example be. Like, I can see us asking something related to the Taylor expansion things they do. Like, what's the point of that? How would you, if you know a method has a certain order of accuracy, then how would you confirm that in MATLAB, for instance? Because that's something that was done for homework. Let's see if I'm. I don't think I would ask anything from one in the notes. Let me take another look at that. Okay, because chapter 1 didn't really get into the. Well posedness is an important concept. I could see asking about that. Okay. All right. Here's some things of interest from chapter 1. It's not much of a chapter, but well-posedness, like what I literally just said. Another important concept that came up was the dispersion relation. That's something that ended up playing a role in the first homework problem. Because basically that's what you were getting. Okay. See, I'm not going to ask about fundamental solutions or maximum principle or anything like that. Okay, Duhamel's principle. Okay, yeah, so none of that. So really, okay, don't. So well-posedness was section 1.3. 1.4, 1.5. Okay. Oh, and also. Classical versus weak solutions. So really it's sections 1.3 to 1.5 are the only parts of that chapter I could possibly ask something about. All right. Also, I'm not looking for this to be some big long ordeal, even though we're only 4 of you. No. All right. Again, I know you've all suffered plenty. Okay. Does anyone have any questions about final or what might be on it or? Okay. Okay. So anything else I need to mention? Okay. As far as finite difference goes, well, we pretty much saw one approach to that. One thing with regard to finite difference and spectral, boundary conditions. Like for spectral methods, we saw very different ways of handling problems that had periodic boundary conditions versus not. And also when we had Dirichlet versus Neumann boundary conditions, how do we handle, like Dirichlet conditions turn out to be much easier to handle for finite differences than for Neumann conditions did. So there's a section of notes in particular for boundary conditions for finite difference. Let's see where I put that. Or finite difference methods 2.2, where it shows how a Neumann boundary condition was handled. Okay. Okay. Well, if you want to get it out of the way this week, well, you might schedule on the door, which is pretty jam-packed. Although Friday, not so much. There's a faculty meeting, and not much else. And then finals week, I will not be running my regular meeting schedule. And for each of you may want to meet once anyway as far as research is concerned, but otherwise it's very free form. And I'll be around every day. I'm not attending commencement. No, it's miserable in that cap and gown for ever. Just,
Can I tell you if you have to come? Or
the rule is we have to attend once per year. So we pick fall or spring semester to go. So I guess by not going in the fall, I have to go in the spring. Let's see. Well, yeah, I do have a PhD student graduating in the spring. So well, here's a really stupid part. Like, if I have a PhD student graduating, then I'm not attending a ceremony. I'm participating in the ceremony because I go up on stage and I'm a student and I put the doctoral hood on them. And strangely, that does not count towards the. So like. Oh, does that mean I have to go in the fall?
Yeah. I was like, you have to go.
I'll see if I can slip by.
Because he's participating in the spring, so that means he has to attend the fall.
Oh God, that just ruined my week. Or next week.
Yeah, this fall.
Next week.
Okay. I'll play dumb and say I didn't know that it worked that way, but that did come up before. That I hooded someone in the fall, and then the chair at the time, Dr. Shore wasn't here yet, was saying, and I still had to in the spring. I said, well, no, I'm going to Hong Kong for a conference. Like, oh, okay, we'll go. Yeah, so, no, because they really don't like it. It's an administration considers it an embarrassment when that area in the back of the arena where the faculty are supposed to be, if that's too empty. So we really want to make sure that people are showing up to all ceremonies. But the thing is, now in the spring, they now have separate ones. Like we have a graduate one on Thursday night, and then the undergrads on Friday, and then the one on the coast on Saturday. So there's 3 ceremonies in the spring.
I guess that's bad for you, but
Well, I wouldn't have to attend all 3. I would.
I mean, it's a
So
lot
could you
cheaper
participate in one and then go to another?
I should try that.
Yeah.
Yeah. Okay.
Just go to like the
Yeah. Now the thing is, I know that when that rolls around in May, when I'll be just as over it as I am now, I'll be just as not in the mood then as now. But I guess I'll be back into a corner. So, yeah. Okay. So in other words, if you want to do it on Friday the 13th, you'll still be okay. That's what I'll tell Dr. Schroeder. If you want to put it off that long. Obviously, that's the furthest it could be put off because the grades are due Monday the 16th. So, my God. That's the one thing, that's one saving grace, at least we know there's an absolute end to all of this. So,
Monday the 16th is when grades are due.
yes, that's right, because all of you are teaching, so you have to, I imagine you've been told about this, or,
No.
no?
Right? I don't know anything about it. Maybe
Or I guess for all 3 of you, Miss Zones or Miss
I mean, it's the same
McCardle
as
is
like how midterm or interim grades were in there, right?
well, did you do that? Okay, yeah, it is the same process.
Okay.
Okay, so,
Pretty sure all of them.
okay, yeah, Monday the 16th at 11 a.m. is when they all have to be done. When was 101 have her final? Oh, but isn't it this week or something? Or
Their finals
next week.
oh, okay. But you still have to go through for partial credit.
I don't do.
Oh, okay. Okay. Okay, Miss 101L. Okay. Okay, but because you have one section,
Yeah.
so you have the hardest of all. Okay, of course. Okay. And what's so silly is it's always been the Monday after finals at 11 a.m. And they'll send out many nagging emails. But one semester they made it 8 a.m. And I don't know why. And I think a lot of people missed the deadline, so they changed it back the next semester. Well, it's just like 1 year, like because we get Mardi Gras off on Monday and Tuesday, and 1 year they gave us only the Tuesday off because it's the actual Mardi Gras day, and expected students to be in classes on Monday, and then they went back to doing it the other way. Yeah, they never figure out what they want to do to us. So it's a divergent sequence.
Think on Mardi Gras on Tuesday.
What?
Think on Mardi Gras on Tuesday.
Yeah, yeah.
It's such a Mardi Gras thing to do. Make it in the middle.
Yeah. Well, and this coming Mardi Gras, I'll be freezing up in Dartmouth giving a talk. Yeah. So, well, actually, okay. So as far as the homework goes,
Yeah, when is that due?
okay. So
You need time to grade it, don't you? You can't like turn it in the last day.
For you guys, it's easier, just because I've been able to keep tabs on all four of you and know how you are doing with the problems. So it's not something like I'm going to get something that you send me and it's like, oh, I've never seen any of this before. I've seen it already. So the grading is kind of moot for the most part. There may be certain things on problem one that might be different, but or things that were done on paper. But as far as the MATLAB goes, I think it's going to be pretty trivial from a grading standpoint. But the thing I want to talk about the homework is because we have 6 problems in total, and I want to make sure I want to make sure that everybody's aware of this because it's something I thought of recently. Okay. Okay. I struck out a part of a problem. So 5, problem D is it comes in 2 parts, Roman numerals 1 and 2. Do not do that because I think if I had to do that one, some of you, or maybe all of you, would want to make a voodoo doll of me and go to town on it. Because it's a very Mardi Gras thing to do. Okay, so
Is there a number 7 that's omitted too? Wasn't there something else?
yeah, so that problem was deleted also.
Oh.
Yeah, so it's problems 1 to 6, and I know the 4 of you. Well, I have an idea of where the 4 of you are with the homework, and all of you have a significant distance to go. Some more than others. But you also have other things going on. Some of it related to me and some not. So. If it's like I'd ideally like to have everything, of course, by the end of finals week, just so there's time to give it a look over and put it in. If it's getting close to that point, and there just hasn't been a time, just come talk to me. So don't worry about this. I'm definitely not looking to give someone a low grade, especially if they're willing and able to do the work. Because I've spent all of last week, but it's supposed to be my relaxing Thanksgiving break, dreading this week and next week, just because of a mountain of things that I have to do, mostly related to grading mostly for 460, 560, for 20 students. And so I figure if I multiply that by, I don't know, some real number greater than 1, that's where you guys are at. And yeah, it's something that I'm concerned about with regards to my responsibility. It's like, okay, everything has to be done by a certain point just to get the grades in, or else. I'm not really sure what the or else is. It's probably not something as bad as we fear. Well, I know of grades. Sometimes I haven't, but sometimes other instructors haven't got the grades in on time. And so they get them in as soon as possible afterwards, and it's kind of a pain in sore to do it, but it gets done. And of course, certain people are going to be mad at you, but it's no. But the same thing goes for what I have here. I don't want this class to be the thing that sends you over the edge. So do your best. Because if things get really rough towards the end, just talk to me about it. So. Okay. And it goes for you too, Jessica. So, okay. All right, so questions about anything? Okay. All right, I have a little less than an hour to cover the important points of a whole chapter in these notes. Of course, the whole chapter is only 8 pages, and there are certain parts that I'm not going to touch. So, hopefully it'll be okay. Okay. And yes, I was looking around here wondering, where's the chalk? Where's the chalk? Yeah, it's in my hand. So, of course, I do that every so often with my phone. So, just tell me you've all been there too, and we'll move on. Okay. All right, so time-dependent problems. Okay, so we have so suppose we have a problem that's of this general form. So the UDT is equal to LU. All right, so for x in some domain, omega, and positive time. And then we have, all right, so that's the PDE. Then we have initial conditions. All right, so the value of solution at time 0 is some given function. And then we have boundary conditions. So here I'm assuming Dirichlet boundary conditions, although it could be something else. And this is for x only on the boundary of omega, like the endpoints 0 and 1, something like that. Okay. Now, L, so this is a linear PDE. We could talk about nonlinear, but I won't get into that here. Now L is called the spatial. Yes, it's spelled with a T, not a C, even though it comes from space. But that's the English language for you. I'm sure in 20 years it'll be spelled with a C anyway. Just from so many people misspelling it. Can you imagine if math evolved that way? I mean, the English language is constantly degraded because people say a word or spell a word wrong, and a dictionary throws up its hands like, oh, okay, it's fine. You could do it that way.
People spell it S-P-A-C?
Yes, I've seen it many, many times.
Wow.
Okay. So, at least there's...
Wow.
Yes, at least there's still some outrage left. But can you imagine if math evolved the same way? That, like for instance, if so many people were doing, I don't know, like square root of x squared plus y squared equals x plus y, and finally math threw up its hands like, okay, fine, it's correct.
Is that what happened? Why it's not called maths? Why is it everywhere else in the world called? Why is math called maths with an S on the end? Maths.
I wonder if that's similar to why we're practically the only country in the world that doesn't use a metric system. I don't know. But again, even in the UK, it still uses the English system. They call it maths also.
Yeah. It doesn't matter.
I don't.
We can talk about it. Sorry.
No, but it's. I'm gonna look that up.
I want to know why.
I think they're wrong.
Everyone else calls it that though.
It's mathematics, not mathematics.
Maths. The maths.
But maths is a sensible abbreviation of mathematics. So
Gerald's attorney.
I'm not gonna cover anything.
Okay.
Alright. Okay. Alright. So some key examples of L. Well, one example we've seen already. The Laplacian. And as all of you know, I like to work with operators like this, except with some coefficients. Okay. Or from first order equations. Dot product coefficient with the gradient. So this is seen in advection equation, so wave propagation problems. I am still recording, right? Okay. Okay. And then another one is a fourth order operator. So it's Laplacian of the Laplacian of u. So this is called the biharmonic. And some of Dr. Tian's research deals with this kind of equation. When we have this with UTT, so second order time derivative, fourth order space derivative, that's called the beam equation. Which seems to me, from my standpoint, my research program seems to be a cursed equation because multiple times I've only had some student work on it and something happens and nothing gets done. I think it's a pretty important equation because it helps you determine if your building is going to stand. Okay.
But the biharmonic, is that LU or just L?
Well, I have to put a U here because of a U here.
Oh, okay.
Yeah. Whereas it was, oh, okay, this is also the L and U because of the U here. All right. But sometimes it's convenient to express the operator just like that without an explicit U. Okay. Now, when we decide to neglect UT, we just assume that UT equals 0. That means the solution is not changing over time. So, if we decide to just neglect that, that is called a steady state problem. And that is useful, because we can try solving that, which would generally be an easier problem. And that might be how the solution behaves over, like what it converges to eventually. But now we want to try to actually include time and see how the solution changes over time. Okay. Now, here I've written UT. Only the first derivative with respect to time. But if you have a problem like this, UTT equals LU, how you would handle that is you could rewrite it as a first order system of PDEs. PDEs that only have first time derivatives. So what I would do in this case is V equal du dt. So then I have ut equals V, and then Vt, which is UTT, is equal to LU. Or I can write it this way. UV as a single entity with respect to time is okay, 0 identity L0. So if you think of UV as a single entity that just has multiple components, and it's still the same form, UT equals LU, which is that U has multiple components now. All right. So then you're computing U and UT together. And yeah, the research, Bailey, that's what we do. Okay. So that's why, for purposes of discussing methods for time-dependent problems, we can just focus on this case. Okay. So what ends up happening is, and it's not always done this way, but how we generally treat a time-dependent PDE. So how numerical solution proceeds. First, we perform spatial discretization. So that is the same kind of spatial discretization we've already seen. You have a grid in X. You choose a spacing like your H or delta X. Space derivatives by finite differences, center difference and all that. So all of that is exactly the same as we've seen before, but you leave the time derivatives alone. So a result of that, instead of having just a straight AU equals F problem, we wind up with U prime of T is equal to AU of T. So A is a matrix that comes from the spatial discretization of L. It's the same kind of matrix that you've seen in the homework. Like for instance, if it's a Laplacian in one dimension, it's your same old 1 over h squared times that tridiagonal matrix. All of that's the same. It's just that now instead of AU equals F, you now have this system of ODEs to solve. So to solve a system of ODEs, you use some time-stepping method. Okay. Now, this entire approach that I described, where you do spatial discretization of a PDE like before, and then you wind up with a system of ODEs to solve, and you go ahead and solve that, that is called the method of lines. Okay. So the name comes from the fact that each element of U of T is the solution at a particular x value, but for all time. So in your whole space-time domain, that includes both x and t, you're picking one line in that domain. Fixed x value, t starting from 0 and increasing. So each component of this vector u of t is a solution along a line in the domain. Then again, if we go back to really, really, really low-level math, I shouldn't say line. If I'm talking about t only being greater than 0, we don't call that a line. What do we call that?
Segment?
No.
Wait.
If I had a particular ending value for t, then yes, that would be a line segment. But if I have t starting at 0 and going off to infinity,
An array.
what?
An array.
You're so close. Not array.
Array.
It's
array.
yes. Okay. Yeah, because you said an array.
An array.
Yeah.
A array.
Okay.
Sorry.
Okay. Well, that's our first. It was on first routine for the day. Okay. Yeah. So we should call it the method of arrays, but that's never going to happen.
Honestly, that's like the only thing I'll ever remember from high school math is that geometry class and that lady always talked about arrays and lines.
Interesting.
Yeah.
Well, yeah, I remember writing all these proofs based on postulates and so forth. And all the maths just go on. So now when I say proof, you think real analysis and not nightmares. So okay, now the funny thing that's happening now as I get to this point where I'm about to tell you about certain time-stepping methods that we would choose at this point. I'm going to go through certain established time-stepping methods, like the ones I wrote on the board before. Runge-Kutta, the one-step methods, multi-step methods. And there's one time-stepping method that would be, at least for all of us here, conspicuous in its absence, my own time-stepping method, a Krylov subspace spectral method. I'm not going to cover that because that would take way too long, but also because it's not something that you would find in a textbook yet, hopefully. And I was just thinking, it would be really nice if someday, a long time from now, when someone is teaching this exact topic, that they'll talk about certain time-stepping methods, and that will be included on the list. But I'm also thinking about how with one of my undergrad researchers, I'm having her examine a method for solving ODEs, not time-stepping method, but method for solving a cyclolinear ODE. It's called Allen's method. That was developed back in the 50s. And I only heard about it from some guy I talked with years ago who was a student at that time and happened to know about it and told me about it. And other than that, I looked it up. I tried Googling it, found almost nothing at all. It's just forgotten. So someone developed a method, went through time, it actually works pretty well from what little I saw, and no one knows about it anymore. And so I'm trying to bring it back and see, like, okay, let's really look at it from today's point of view. Is this something worthwhile, or is it something that, in fact, should have been forgotten? Because sometimes methods that were dismissed when they were originally developed came in vogue later because of technology changes. Like we have parallel computers now. So methods that may have been inefficient for a computer with one processor are now more efficient when you have many of them. So it's important not to have these things just forgotten altogether. So I have whatever remains of my career to try to make sure that my time-stepping method does not meet that kind of fate. It is not completely forgotten. Like, oh, here's some crackpot from the early 2000s who wrote some papers on it, and oh well. So, well, I guess you guys will be around to see that. I won't be, so. Okay, so so how do we solve this kind of system of ODEs numerically? Although two of you have learned about that from 461, and the other will learn about that next semester in 561. Okay, so the idea is, all right, so this would be a more general system of ODE. The system I gave before is a linear system. This system is allowed to be nonlinear. So the time-stepping methods I'm describing will apply in either case. So here's our ODE, general first-order ODE, so F is given. And then you have an initial condition, y0 is equal to y0. All right, the boundary condition from whatever PDE has already been taken into account from discretizing spatially. So we no longer think about boundary conditions. We only have initial conditions. Okay. Now, so I'm just going to go through a catalog of methods. And any discussion of time-stepping methods should begin with the simplest one of all, and that is either explicit or forward Euler's method. Now, this would also be Euler's method by itself, but for clarity, it's referred to as either explicit Euler or forward Euler. So what you do is you replace y prime so actually, before I write this method down, I need to give some notation. So in general, if I have y with a superscript n, it's not an exponent. It's an approximation of the solution, the exact solution y, at time tn. And tn is equal to n times delta t. So just as with previous PDEs, we had a spacing in x. So that we called it h, or delta x. So now we have a spacing in time also.
What is that symbol
Which symbol?
before the delta?
This?
Yes.
I just letter n.
Oh, never.
Okay.
Like, this is new.
The funny thing I was thinking when I was writing this, it's like, how many, and pretty much only upper level students who have a world's rocked when I write this, they're so accustomed to this being an exponent, not tell you it's not anymore. And that's why sometimes it's included in parentheses, like for iterative methods, but yeah. Okay, so forward Euler is yn plus 1 minus yn over delta t. So this is my approximation of the time derivative at, or should write it this way, y prime at tn. It's approximated by this. And that is equal to f evaluated at time n. So that's all we do for forward Euler. We just replace the time derivative by a forward difference. So that's where the name forward Euler comes from. Okay. So then what you can do is you can rearrange this because everything here is known except yn plus 1. So we just plug and chug everything on the right side to get the value of the new time. Because you're given y0, that's the initial data. So we just grind this out. And so then you have this to plug in for the next time step, and so on. So very simple time stepping method, not particularly effective, but at least it's easy to implement. And what's really sad is there's so many very sophisticated time stepping methods. It's not just my own, and the other ones I'm going to talk about. But so many researchers, if they have a need to solve an ODE and they don't have like MATLAB handy, if they want to code it themselves, they'll just do this, as awful as it is, just because it's easy, and it drives me nuts. Okay, now, okay. Second method I'll talk about is very close to that. So it's the opposite in a way, implicit or backward Euler. So now what you do is you replace the time derivative by a backward difference. And everything is evaluated at time n plus 1 rather than time n. So now what's interesting is part in the middle here, it's exactly the same, except now it's being used to approximate the time derivative at time n plus 1. So now it's a backward difference. Rather than a forward difference. And that is equal to f, but now it's evaluated at time n plus 1 rather than time n. So this is what gives the name backward Euler. So now if I rearrange this, it's almost the same as before. But now we have n plus 1 throughout the call to f. Now, notice we have yn plus 1 on both sides of the equation. So we don't have an explicit formula for yn plus 1 anymore. We have to solve for it. Now, if this is a linear system of ODEs, that's not difficult. Like, for instance, if f was just multiplying by a matrix, we'd be dealing with an inverse matrix. Not a big deal. But if f is a nonlinear function, then we have more work to do to try to solve for yn plus 1. We have to solve a system of nonlinear equations. So you have to use certain iterative methods that are used for nonlinear equations in general to get yn plus 1. And what would be some of these? What are some methods, fundamental methods out there, like ones that I cover in class, for solving nonlinear equations, Sarah? It's only because you've just been seeing them.
Yeah.
Or maybe Ellie can help. She saw me a year and a half ago. You missed a boat on this one. You've never seen it in any class I've taught. So, in other words, root finding methods. Okay.
It
Yeah.
starts with a B?
I think that one would not help us, but okay.
What is that one called?
Bisection.
That one, yes. Okay.
Since bisection is only useful for one-dimensional problems, but
Okay.
so any of the other three methods that I covered?
Any of like the quadrature?
No, wrong chapter. Yeah, so root finding.
No. Problem? No.
That's the integration method.
Yeah.
Newton's method.
Yes.
Okay. What?
Oh, in your book.
Yeah. I had to look at it there, but not for a class. Does that jog your memory for any of the other ones?
No, like the Newton codes.
Oh, no, that's also integration. You seem to know the integration methods quite well, so that's good.
It's been a lot.
Okay. CCAT method, which is probably the one most often used because it doesn't require an explicit derivative. Also, fixed point iteration. Okay, so time-stepping methods break down into various categories, but two categories in particular are explicit and implicit. So explicit method, I like to call them plug-and-chug methods because that's what you can do. You can plug and chug with old info on the right side to get the new value on the left side. Implicit methods, you must solve an equation to get the value at the new time. And if it's a nonlinear system of ODEs, then you must use some iterative method, such as Newton's. The nice thing, though, about using those methods, that seems like a lot of work for just one time step. But those methods require an initial guess, and you already have a good initial guess right here. So chances are it's going to converge. What a lot of methods do is they just perform one step and move on. So that's good enough, especially if using Newton's method because it's quadratically convergent, it's very rapidly convergent. Okay, so those are the simplest time-stepping methods. Now, okay, let's talk about the other. I'm going to go a little out of order in the notes and talk about certain categories of methods just to make sure I get those in. And then I will talk about error analysis. Okay. So, third category of methods is really the generalization of what we see here. Are Runge-Kutta, often abbreviated as RK, methods. So these are a lot more complicated than Euler, but they also deliver more accuracy. I'll talk about order of accuracy a little bit later. So I'll give a general form for Runge-Kutta methods that's somewhat similar to what we have for Euler's. So new solutions equal old solution plus delta t times a sum of some coefficients times these vectors kj. Now, these values, the k's, each one of them is going to be an evaluation of your time derivative from your ODE, your f, at specially selected time values and certain solution values that are passed in.
Is it TJ?
It's not a comma. I think it's a comma.
This is a comma. Okay.
Oh, wait, how many commas? No, that's a different.
So far there's been one comma. Okay. Oh, I need a different letter here.
No.
A-I-J K-I. Okay. So we're evaluating f at certain carefully selected t and y values just to try to improve accuracy. So each one of these vectors here, these k's, is called a stage of a Runge-Kutta method. So j is equal from 1, 2, up to, up to s. So s is the number of stages that you have. Now, technically, forward Euler is a Runge-Kutta method where s equals 1. So it's like a one-stage Runge-Kutta method where this part would be 0 and this part would also be 0.
Forward Euler
Yeah.
is Runge-Kutta when s equals 1.
Yes, yeah. So forward Euler is a one-stage Runge-Kutta method. Okay. Okay. Now, let's see. Do I have some? All right. For some reason, implicit Euler is also described as a Runge-Kutta method. But I don't think that's consistent with the form that I just gave. Okay, so C would be 1. A would be 1, and B would be 1. Oh, interesting. Okay. So, all right, so I'll list off some. God, I'm chewing up all my time here. I may have to cover some of this on Wednesday, but okay. So, some examples of Runge-Kutta methods. So we have forward Euler is a Runge-Kutta method. S is equal to 1, so that's the total number of stages. And you have B1 is equal to 1, the coefficient down here. Oops, sorry, Jessica. Okay. And then down here, we have C1 is equal to 1. So we have Tn plus 1 down here. And then I have A11 is equal to 1. So this also goes from 1 to S. Oh, I'm sorry. That's totally screwed up. This is backward Euler. Okay. With these coefficients. Whereas forward Euler also falls in a category where B1 is again equal to 1, C1 is equal to 0, and A11 is also 0. Okay. Now, more interesting Ronconer method is explicit midpoint, which can be written this way. K1 is f of Tn, Yn, just like forward Euler. K2 is equal to f of Tn plus delta t over 2, so we take a half time step, and then Yn plus delta t over 2 K1. So it's like taking forward Euler for a half time step. That's what's going on here. So this is an approximation of y. Sorry, I have superscripts where I need subscripts. Yn plus a half, because we're taking this half time step, everything of delta t over 2. And then Yn plus 1 is equal to Yn plus delta t times K2. So K1 is only used right here. That doesn't play a role in the final value of the solution. Okay. All right. On the other hand, since I mentioned explicit midpoint, there is an implicit midpoint that only has one stage, K1, which is equal to f of same time value as K2 before, Tn plus delta t over 2. And then I have Yn plus delta t over 2 K1. So notice I have K1 on both sides of the equation. So you must solve for it using some iteration. And once you have it, then Yn plus 1 is equal to Yn plus delta t K1. Okay. So on one hand, one less stage than explicit midpoint, but that one stage takes more work. It's good to evaluate f more than once, or possibly several times, to have a convergent iteration. Now, you don't necessarily want to iterate all the way to convergence, because there's other sources of error. You're not going to get the exact solution of the whole thing anyway. So you might as well stop early and not waste time on iterations that don't really improve your accuracy for the entire solution. Okay. And then there's, let's see what I have here. A couple more Runge-Kutta methods. have be method E be explicit trapezoidal method. Or as I found in the UK, they call it trapezium method. Seems like it's something out of a circus or something. Okay, so for that one, K1 is defined as before. And then K2 is an approximation of f at time n plus 1, where for y value, we take a forward Euler step. Yeah, so delta t, K1. So in fact, this is a time step of forward Euler right here to get an approximation of y n plus 1. But then that's fed into f again to get K2. So the idea is to get an improved y n plus 1. So now we take the average of these two. All right. Now, although it's a real pain to write out, I'm not going to write down the whole thing. It's the most popular Runge-Kutta method, fourth order Runge-Kutta. That performs 4 stages. So we have K1, 2K2, 2K3, plus K4, where okay, fine, we'll write it out. So there's the first stage. That's the same as the first stage you've seen in other methods. K2 and K3, all this, I feel like my hands could get out. It's on page 40 in the notes. Both K2 and K3 have in common that they take an approximation of a solution at the midpoint, Tm plus a half. But with different approximations here. Because this stage uses K1, whereas K3 uses the same. Yeah, that's right. This short piece of chalk is making my hand cramp up. Whereas the third stage, same time value, but for the y part, uses K2. And then finally we have K4 that uses Tn plus delta t, so that's at time n plus 1. And then we use K3 down here. All right, so all 4 of those stages are combined to give an approximation of yn plus 1. Now, what's weird is, look at the coefficients here. 1, 2, 2, 1. Makes sense they add up to 6. But both of these come from approximating solution at the midpoint in time. Now, there's a well-known integration rule, because basically these are time integration schemes. There's a well-known integration rule that puts 4 times the amount of weight on the value at the midpoint than on the ends. And sorry to put you on the spot, Sarah, but since you seem to know a lot about integration rules, you walked right into this one. Yeah, what's the integration rule? We saw that weights the middle value 4 times compared to the other ones.
Was it the trapezoidal, the quad,
Wait, which one of those quadrant rules does that?
the composite?
The No. So then the non-composite version had a coefficient pattern of 1, 4, 1, just like this. But in the composite version, I have 1, 4, 2, 4, 2. Yes, it's Simpson's rule. Yeah. So it's kind of where it comes. It's similar inspiration anyway. Giving a midpoint that much weight gives a good accuracy. Okay, so those are certain Runge-Kutta methods that all evaluate f at several time values between Tn and Tn plus 1. But there's one more, and I think I have just enough time for it, major category of time-stepping methods. I mean, like I said, they break down many ways. There's implicit, explicit. There's also one-step and multi-step. So far, everything I've talked about is called a one-step method. And what I mean by one-step is it only uses information about the solution on the time interval Tn to Tn plus 1. So what happens is you take a time step, like say from time 0 to time 1, okay? Then when you go from time 1 to time 2, everything that happened from time 0 to time 1 has been forgotten. You don't use it anymore. So you're only focusing on that current interval in time. But that information about the solution can be useful because it's giving you a trajectory. So multi-step methods use information about the solution from further back in time. So all these methods have a general form, just like Runge-Kutta methods do. Okay. So we have a linear combination of y's on the left side is equal to delta t times another linear combination of f values on the right side. So my notation here, f n plus j is equal to the function f evaluated at time tn plus j yn plus j. So the number s here is the number of steps. So s is going to be greater than 1. That's what makes it a multi-step method. Okay, so they all have this form. Now, it's implicit method if and only if the first of these beta coefficients, or actually the last one, beta s is non-zero. Otherwise, it's going to be explicit. Because if it is, the idea is all of these y values are known, except for the last one, y n plus s is the one you're trying to compute. So if beta s is non-zero, then you have y n plus s here in the call to f. So you must solve for it. Okay. Now, there are certain classes of multi-step methods. There's Adams, Bashforth. So these are explicit methods. So the idea is alpha n plus s is equal to 1. Alpha n plus s minus 1 is equal to minus 1. Generally, all the alphas must sum to 0. All other alphas must be 0. So the left side is pretty simple. And then beta s must be 0 because that's what makes it explicit. And then Adams Moulton Yes, these are covered in 461. So, same conditions on the alphas. So that marks all Adams methods of any kind. If beta S is non-zero, that makes a method implicit. So those are the two families of Adams methods. Next, I think the way it happened was that Adams and Bashforth collaborated to invent the Adams-Bashforth methods. And then it's really Moulton himself who did the Adams-Moulton methods, but since they were so close to Adams' methods, Adams' name is mentioned too. Okay. So in fact,
Is that this would be alpha n plus s plus 1 for the negative 1 and 1?
n plus s
minus
1. Yes. Whoops. Okay. All right. I'll give examples of one of each. Both. Okay. So Adams-Bashforth. Okay. So I'm debating my usual board rhythm here, but I always do that anyway. So yn plus 2 is equal to yn plus 1 plus delta t. So this is a two-step method. Okay. So notice fn plus 2 does not appear. So this is an explicit method. So the idea is that after time n plus 1, everything on the right side is known. So you can just plug and chug with them to compute yn plus 2. Notice also, look at the coefficients. 3/2 and minus 1/2. Coefficients on the right side. The coefficients of the f values sum to 1. So that's an Adams-Bashforth method. An Adams-Moulton method, which is, okay. Actually, this, okay. Didn't like that example. That's a one-step method. Here's a two-step Adams-Moulton method. Okay, so we have 5/12 fn plus 2 minus 8/12 fn plus 1 minus 1/12 fn. Okay, so both these are two-step because n plus 2 is the highest index that occurs. That should be a plus, not a minus. Okay, so the coefficients, 5/12, 8/12, minus 1/12, again, they sum to 1. But because we have an fn plus 2, which we did not have here, that makes it implicit. Oh, what?
What does that sum to 1?
13/12 minus 1/12? Okay.
I was still subtracting 8.
Oh, yeah, okay. All right, so that was my fault. Okay. All right. Okay. And then another kind of multi-step method is BDF, a backward differentiation formula. And too lazy to write on full. Okay. These are actually used some in certain MATLAB ODE solvers. So the idea is, instead of, so what happens is, Adams methods come from approximating, they work with the integral form of the ODE, because you have y of tn plus 1 equals y of tn plus the integral from tn to tn plus 1 of f. So the ODE, the exact ODE, you integrate both sides of it. And you get, from Tn to Tn plus 1, you get this. So Adams' methods come from approximating this integral using a quadrature rule. And a very strange quadrature rule, because they actually use time values that are outside the interval. So they go back, because multi-step methods use values back in time. Backward differentiation formulas work with the original form of the ODE, and they approximate the time derivative. So Adams methods are based on the approximating numerical integration. BDFs are based on numerical differentiation. So backward differentiation formulas, they're always implicit, no matter what. And beta j is equal to 0 for j less than s. So there's only one beta on the right side, and there's more going on the left side. So as an example, okay. So I think I'm mistaken. Okay, never mind. So an example of a two-step BDF is 3yn plus 2 minus 4yn plus 1 plus yn. The coefficients on the left side will sum to 0, like they normally do, for any multi-step method. Over 2 is equal to delta t fn plus 2. Okay. So this comes from a finite difference formula for approximating a derivative using values of time n, n plus 1, and n plus 2. And then that's equal to f at time n plus 2. So here the complexity is with a combination of y's, the alphas. Here, Adams' method of complexity lies in getting the betas. Okay. Oh man, I've already gone past time. Okay, that's fine. I'll stop. But so I'll take some time Wednesday to talk about order of accuracy, stability, things like that. But we should have time for homework also. I'll just have to not yammer as much.